Week 4, Problem 5. In this problem, you have two painters standing on a beam that's being suspended from two wire ropes, one at either end, and we're asked to find the tension in each of these wire ropes. So let's just make some notes in the diagram here about what we know. The problem gives the weight of each painter as 180 pounds. So I have a 180 pound force here at point C, and staying with the conventions of the Cartesian plane, I'm going to show that force as a negative 180 because it's downward. Same thing here at point D, force of negative 180. The beam has a weight of 100 pounds, which we can think about as acting right in the center of the beam. So if we look at the overall length of the beam, 2 feet plus 6 feet plus 4 feet, the overall length of the beam is 12 feet. And the weight of the beam we can think of as acting right at its center, negative 100 pounds. And we can get away with that because the weight of the beam is uniformly distributed. Okay, and I'll make a note here that that distance to the center of this beam, this center line here, 6 feet. Let's think about what else we know. Okay, that's all that's given in the problem. Now, the way you have to solve this type of problem is you have to pick a point where there is a pivot. And I'm going to choose for the first part of the analysis to put the pivot at point B here, as though this whole assembly is hinged right at point B, so that if this wire rope from F to E were to break, this whole thing is going to pivot down in this this clockwise motion. I'm also going to label these tensions in these wire ropes. So I'll call this T sub AB for tension in wire rope AB, and I'll call this tension sub EF for tension in wire rope EF. Now let's just think about some of the things we know. There's some really simple stuff you can do, like the sum of the forces in the x direction. Well, we don't have any forces acting left or right, so that simply equals 0, and that is to say that there's no left or right force in this system. How about the sum of the forces in the y direction? Well, we have the weight of the first painter, which is negative 180, plus the weight of the second painter, which again is negative 180, and it's negative because it's in the downward direction, plus the weight of the beam itself, which is negative 100. All of those are downward forces. What's providing the reaction, the upward reaction to that? It's the tension in the wire ropes. So plus the tension in the wire ropes, so tension AB, plus the tension EF. And what does all of that have to add to? Well, that all has to add to 0 because this is in static equilibrium. So another way to think about it is you have 460 pounds of downward force. The upward tension must total to 460 pounds. Let's make a note to that effect, just so that we remember. T sub AB plus T sub EF, by definition, has to equal 460. Now let's think about moments, and let's think about the sum of the moments about point B. And actually I'll come over here because this is going to be a little bit more writing. So sum of the moments, so sigma m sub B, equals the moment generated by, we'll call this guy painter number 1, this guy will be painter number 2. The moment generated by painter number 1 is 2 feet times negative 180. The moment generated by the weight of the beam is 6 feet times negative 100. The moment generated by painter number 2, well, if this entire distance is 6 and he or she is 4 from the end, this distance in here has got to be 2 feet. And again, it's the distance from point B that we're interested in. So 6 feet plus 2 feet is 8 feet times the weight of negative 180. And if you look at, these are all negative moments. They're all attempting to roll this beam in a clockwise direction. So if this is going to be in static equilibrium, there has to be a positive moment. And that positive moment is created by the tension in wire rope EF. So how far is wire rope EF's attachment point from point B? Well, it's 12 feet, plus 12 feet. And the tension in EF acts in a positive direction. So if we add all of these moments together, they should all sum to 0, since this is in static equilibrium. Now if you look at this, basically we have all of these are constants with the exception of the tension in wire rope EF, which is what we're going to calculate now. Let's simplify this by getting each of these into, let's simplify all these products, and then we will push it around using some algebra. Okay, so 2 times negative 180 is going to be negative 360. And really the numbers for this are pretty easy to work with. Maybe we'll just do it manually. Negative 360, and these are moments. So the unit here is foot-pounds, plus negative 600 foot-pounds plus 8 times 180. Okay, so it's negative 180 times the distance of 8 feet, negative 1,440 foot-pounds, plus 12 times the tension in wire rope EF has to add to 0. Now, we're trying to get the tension in wire rope EF by itself. So how are you going to do that? Well, you're going to add all of these to the other side, and then you're going to divide by the number out in front of it. So if I rearrange this, if I say tension EF equals something over 12. I'm dividing both sides by 12. Well, what does it equal? It equals 360 plus 600 plus 1440. And remember that these numbers will become positive now because we're pushing them over to the other side of the equation. We're basically adding the opposites to each of these. Okay, so 2400. And again, if we think about units here, this is foot-pounds, and this is feet. So when we strike the similar units, when I strike feet from each of these, I just get a force in pounds rather than a moment in foot-pounds. Well, 2400 divided by 12, that equals 200 pounds. So the tension in wire rope EF is 200 pounds. Now, a couple of different approaches for solving this. One is, remember that the tension in wire rope AB plus the tension in wire rope EF has to add to 460. So we could simply use this identity and say, look, tension AB plus, we know that the tension in EF is 200, has to equal 460. Subtract 200 from both sides, and we could say the tension in AB has to equal 260. That's one approach, and if you're confident in the first number that you calculated, you can go ahead and do that. However, if you made an error on tension EF, that error is going to also appear in tension AB because they're just simply a sum. So here's an alternative approach to calculating that, is you say, now we're going to make point E the pivot, and we're going to calculate the sum of moments about point E. And the sum of moments about point E are 4 times negative 180 plus 6 times negative 100. Now the last piece here is to look at the moment created by painter 1. And if you think about painter 1, remember that this 6-foot distance refers to the distance between the two painters, not to the center line. So painter 1 is 4 feet left of the center line of the beam. So painter 1's distance is negative 10 feet times his weight, negative 180. And then the last piece of this is the moment created by the tension in wire rope AB. Well, that's at a distance of negative 12 feet. And in this case, the force, the tension, is going to be a positive number because it's pulling upwards. And this entire sum together equals 0. So if we crunch the numbers on all of these pieces, 4 times 180, so remember I'm multiplying a negative times a negative, so I get a positive. 720 pound-feet created by the first painter. And then the second one is just negative 600 times negative 100, so 600. And it's a positive 600. Plus negative 10 times negative 180, that's a positive 1800. Plus negative 12 times the tension in wire rope AB equals 0. So same process to get this separated out. I take tension in AB, and I'm going to subtract all of these numbers from the left side, from both sides, which means I'm going to end up with a negative number on the right side, and I'm going to divide both sides by negative 12 to get rid of this coefficient. So let's see, 1800 and 600, that's 2400, plus 720 is 3120. And again, it's a negative number because I'm subtracting it from both sides. So let's see what number that gives us. And we find through this method that a tension of 260 pounds in wire rope AB. So you see that both methods brought us to the same solution, which is a good indication that the computations are accurate. Of course, the answer key also gives the same numbers, the tension over here being 260 pounds.